Welcome to Calculus and Curve Sketching. You should have heard in class by now references to stationary points as well as points of inflection. Americans spell it like this. If your examiner is a Brit, he or she may spell it like that. Stationary points are, of course, points on a curve where the slope of the line drawn tangent to the curve would be 0. Hence, these two local minimum points and this local max represent x values of so-called stationary points. Somewhere in here and somewhere in here, we see with these red arrows, we've got the concavity changing. We're going from concave up to somewhere in here where we go concave down, and then we're concave down until we get to this area and we go concave up again. So those transition points are referred to as points of inflection. So let's talk about the calculus a little bit more specifically to these concepts. So in red we have a cubic, and I've got it graphed for you here conveniently. And the derivative of this cubic, where you can just see 6x squared minus 6x minus 12, pretty straightforward. That actually is graphed for you in blue. So if you take this cubic, which clearly has some kind of a local max and a local min, and for that matter, somewhere in here there's a concavity transition taking place. If you set that first derivative equal to 0, of course that's your gradient function, and x per x, it is measuring the slope of those lines drawn tangent to the curve, and eventually they are zeroing out, as it turns out, at -1 and at 2, because you can factor out the 6 there, be left with a quadratic, and then factor that guy. Setting each of these factors equal to 0 gives you the 2 and the -1 respectively. So you'll notice that this concave up parabola that represents your first derivative, which you see right here, actually has zeros at -1 and at 2. Well, that 0 of -1 for the first derivative corresponds to the place where the slope of the line drawn tangent is actually 0. And again, that 2, x value of 2, corresponds to the place down here where the slope of the line drawn tangent is actually 0. As it turns out, we're going from concave down, transitioning somewhere in here, to concave up. And note that where that transition will take place, that's going to have something to do with this low point, as it turns out, on the first derivative, which gets into the effect of the second derivative, and we'll see that a little bit later on. So what if you were in a paper 1 context? What if you had to get some feeling for what this cubic looked like? And let's say you do not know what it looks like, and the best you can do is just differentiate it, once again, factor it a bit, and see what you have here. So there is something called the first derivative test, where you can look a bit more closely on each side of the so-called critical values. When you set this derivative equal to 0, you pick up that x equals 2 and x equals -1 are those so-called critical values. They kind of chop the number line into 3 regions, right? 1, 2, 3. I've labeled them that way. Region 1 is effectively from -1 all the way to negative infinity, which is going to be down here from -1 all the way towards negative infinity. Region 2 is just between -1 and 2. And then region 3 is from 2 to positive infinity. So let's grab some test points in each region and check the sign of the derivative to give us a feeling for what the curve might be doing. So pick your favorite test value from over here, somewhere left of -1. Let's grab -4. If you put -4 in there, overall that sign would be negative. -4 in there, overall that sign is negative. We don't really care about the numerical value. We just care about the fact that we've got a negative times a negative because these are being multiplied. And that gives you a positive overall for the first derivative, which tells you the curve is going up. Why is that? Because that would be saying that the slope of any line drawn tangent to the curve left of -1, all of those slopes would always be positive. That's what it actually means. Then between -1 and 2, maybe grab 0. That's your favorite one to grab. 0 in there keeps that factor as negative. 0 in there, there's a transition now, and negative times positive, because we're talking about the multiplication of these two. Negative times positive is overall negative for the first derivative, which tells you the curve's going down, because the slopes of all of the lines drawn tangent to the curve between -1 and 2, all of those slopes would actually be negative, because all those lines fall from left to right. And then just to the right of 2, put in your favorite value. Could put in 100 for all we care, something really, really big and safe. Positive, positive, overall positive curves going back up, and you can see it there. So the first derivative test can be a handy way to sort of look on both sides of a critical value to get a feeling for what the curve itself might be doing. Here is a fourth power polynomial function that's a little bit more involved. You see it graphed here for you in blue. First derivative, pretty straightforward, 6x squared minus 4x cubed. What happens if we set that equal to 0? We can factor out the common factor of 2x squared, and you've got, when you set this factor equal to 0, you pick up x equals 0 itself, and this factor set equal to 0 gives you 3/2, better known as 1.5. So once again, you've broken the number line with these two critical values of 0 and 1.5 into 3 regions. And so what if you started to take a look on each side of those critical values to see what the curve itself is doing by using the positive or negative values of the actual derivative? That's what we're talking about here. First of all, 2x squared straight across the board would always be positive regardless of where you are, because anything squared is positive. Let's look to the left of 0. So anything negative you're putting in, like -1, -2, -5, -20, that's always going to give you a factor here that's positive, and the product of those two will give you a derivative that's positive, which tells you the curve is going up. And you can see that this blue curve is definitely going up, and of course the slopes of any lines drawn tangent would actually be positive. That's what that whole set of information is communicating to you. Between 0 and 1.5, if you grab 1, for example, which is right here, kind of safe to put in, well, that's again positive. We already saw that. 1 put in there keeps that as positive. So as it turns out, positive times positive gives you positive overall for the derivative. The curve is still going up. And in fact, that's what we see. So those lines drawn tangent were all positive until right here at the origin, where they hit 0. But then they keep going and they stay positive. So all we did was transition through a stationary value there that, as it turns out, is also a point of inflection because there's a concavity change taking place there. We'll see that in just a second. So then if you go to the right of the 3/2 that we got here, so this 1.5, again, that guy stays positive. We already saw that. Anything that you're putting in there now, that's going to be guaranteed to be negative. That product overall is negative for the value of the derivative, so that says the curve's going down because the slopes of the lines drawn tangent are all dropping from left to right there. They're all negative past 3.5. So that's giving you a feeling for the curve itself using the first derivative test. If you go a step further and get the second derivative, which going back here is not hard, actually maybe here is better, 12x minus 12x squared, factor out the 12x, and you've got 1 minus x. Set each of these factors equal to 0, you get x equals 0 and 1 respectively. What does that tell you? That tells you that there's a concavity change at 0, and we already saw that, concave down to concave up, even though it was also a stationary value. It's also a point of inflection. And x equals 1 is the other place, and that's going to be right here. You can see in blue your concave up until right about here, namely at 1. You transition and your concave down. So the second derivative can be used sometimes to complement the first derivative test. Hit the pause button, have a read, think that through, and then we'll see where we are. Okay, I hope you spent some time with that. So coming up with the x and y intercepts, let x be 0 and let y be 0. You get x equals 0 itself and x equals -3 pretty quickly from these factors. So in blue, you've got x-intercepts, namely at -3, 0, and at 0, 0, the origin. Let's go back to our function and consider its derivative. That requires a product rule. So first times derivative of second. Technically, the derivative of the second requires chain rule with the derivative of the piece inside being 1. So I put that there for you rather dramatically. So there it is, first times derivative of second plus second times derivative of first. Common factor there, I'm going to factor that out, x plus 3 squared, and I'm left with what you see here, which is 4x plus 3. Set these factors equal to 0, you pick up -3, and as it turns out, -3/4. So in red, I've got two stationary values. These are the places where the slopes of the lines drawn tangent are 0. That's what setting the first derivative equal to 0 accomplishes for us. Go a step further. We'll use this version of the first derivative. Again, product rule with potential chain rule if it comes up. First times derivative of second, that's just linear, so it's just 4, plus second times derivative of first. Once again, the derivative of that guy, to be dramatic, would be looking like that in terms of the chain rule. The derivative of that piece inside is pretty harmless as a 1. So have a look at that, clean it up a little bit. As it turns out, x plus 3 is a common factor, and 2 as well. So I factored that out, and I'm left with some stuff you see here. You can have a look later if you freeze this or listen to it again. We'll set that second derivative equal to 0, and you end up getting, and hopefully you can confirm that you get negative 3 and negative 3 halves. And I've got in green for you that there's two places where the second derivative is equal to 0, and that would be where there's concavity transitions, concave up to concave down, and then right in here we're going from concave down to concave up. So have a think about that. That's it for now. Hope that was helpful, and catch you next time. Bye.